disclaimer before we start this video, I would like to remind everyone watching that I am not a chemist and I am not a physicist. And the title of this chapter is The Chemical Basis of Life. And while the topics we will be discussing, I can easily go into much more depth with, that is not relevant for the purposes of a very general, very intro level biology talk. All right, with that out of the way, please enjoy the following few minutes. Hello and welcome back to Biology for Beginners. As always, I am your host, Morgan. Today, our topic is all about matter. Now, matter can be most simply defined as anything that takes up space and has mass. And mass is essentially how much it weighs. It's a little more complicated than that if you go on to study physics or chemistry, but for our purposes, it's going to be how much it weighs. You think grams, ounces, pounds, you're on the right track there. And on Earth, you can find matter in solid, liquid, or gas forms. Our particular examples here are the ice cubes for solid, liquid water, and the water vapor rising off of the hot spring to represent gas. Now, if you break matter down into its most pure form, you're going to arrive at an element. And an element is a substance that cannot be broken down to other substances by chemical means. And you're probably pretty familiar with at least seeing the periodic table of elements, but that's what all these letters and numbers mean. These are the substances that are the most pure, that cannot be broken down any further. Now, of course, if you go into fantasy books, you hear about alchemy changing elements from one to another. That doesn't happen in real life and basically cannot happen, at least with our current technology, but is very unlikely to happen in the future at all. Sorry to break that to you. Now, there are specific elements that living things just need. And the most basic elements that every living thing is going to need, because they make up the compounds of life, are going to be the oxygen, carbon, hydrogen, and nitrogen. But those are not the only things living things need. When you get down into the very small, less than 0.01%, you get the trace elements, which is an element required for life, but in extremely small amounts. And these trace elements, while they may seem insignificant, if you don't get enough of them, you do end up with fairly large medical complications. You will get deficiencies. Iron, for example, is needed to help make the hemoglobin in your blood. And the reason why you need the iron is it binds the oxygen. So if you don't get enough iron, you can't bind enough oxygen, and things kind of spiral from there. And of course, different organisms will need different elements in different amounts, but it is important to note that specific elements are required, and if you don't get enough of them, even the very small requirements, there can be fairly massive problems at some point. Now, how do you get these elements that you need for life? Do you just walk over to the periodic table, pick up a big square of carbon and eat it? Well, no, it's a little more complicated than that. You're going to get your elements in what's known as a compound. And a compound is a substance that contains two or more elements in a fixed ratio. Every single compound is going to have its own unique characteristics that are very different from the elements that make it up. Some good examples are going to be H2O, or water, which has the 2-to-1 hydrogen to oxygen ratio. And water is required for life on Earth. It is very important, and we will have an entire episode just on water in a couple of weeks here. But hydrogen and oxygen are both going to be found independently as gases. However, when you put them together in this compound at room temperature, they're a liquid. And that is the first difference that you're going to see when you look at that compound versus what makes it up. Our other example here is sodium chloride, NaCl, in a 1-to-1 ratio. Now, chlorine is generally going to be found in a gaseous, poisonous state, and the sodium is a metal. But you put them together, you get this very tasty crystal that goes into our food and is safe for human consumption. But individually, both of these elements would kill you. Now, if you're going to try to at least begin to understand how these compounds are made and how all of this is possible, you have to look at the smallest unit of matter that will still retain the properties of an element. And this unit is the atom. Now, atoms are made up of these subatomic particles, and that just means smaller than an atom. Now, for our purposes, we're only going to be looking at 3 subatomic particles. While I do recognize that there are more than just 3, those are not relevant for our discussions as a biology series of lectures. The 3 particles we're specifically looking at, you've probably heard these words before. We're looking at protons, which is a particle with a positive charge, electrons, particles with negative charges, and neutrons, which are particles that have no charge or are neutral. Now, if you look at the little arrows on my screen here pointing at protons and neutrons, these are the 2 particles that make up what is known as the nucleus at the core of the atom. And the negative electrons kind of buzz around in a cloud outside of that nucleus. And the atom is mostly empty space, since electrons do move very fast around this cloud, and the nucleus is very, very tiny. Now, a couple of things that are important to know when you're looking at what the heck is making up an atom. If you look at the periodic table and pull out carbon, for example, in this little square, you'll see the C that stands for carbon, and you'll see a couple of numbers. Now, the one at the top here is the atomic number, which is the number of protons in a single atom of this particular element. And it is the number of protons that defines the atom. Now, neutral atoms will also have an equal number of protons to electrons because those charges will cancel each other out. So a neutral carbon atom has 6 protons and 6 electrons. And a big theme when you're looking at compounds and atoms is that in nature you want to be neutral, and that is usually the goal of when we get into bonds and forming those bonds, is overall the product is going to be neutral. But we will get into that in a later video. Now, the second number here is the atomic mass of the element, which basically means how many grams per mole of an element. And a mole is kind of like a unit of measurement. It's not quite that simple, but that is more relevant in a chemistry discussion than it is in a biology discussion. But the important thing is that if you were to have a mole of atoms of this element, that is how many grams they will weigh. But you can also look at this as an important number is the mass number as well. And this number is not the same as the atomic mass. The mass number is how many protons and neutrons are in an atom. So if you look at this particular example of carbon-12, it's 6 protons and 6 neutrons. So the number of subatomic particles total in that nucleus is 12. It's a little bit more complicated than that, but that's essentially what you need to know here. And because it's the protons that define the atom, not the neutrons, you can get different numbers of neutrons occurring in the same element. And when you get this, you end up with what is known as an isotope. Now, carbon has 3 very commonly found isotopes: carbon-12, which is the most common, carbon-13, which is a little bit less common, and carbon-14, which is radioactive. Now, radioactive isotopes mean that they're unstable, and the nucleus is going to begin breaking down, giving off particles and energy that can damage DNA and other molecules that are essential for life. But isotopes in general can be useful. Now, radioactive isotopes can be used in things like carbon dating, where researchers look at the proportions of how much of a radioactive isotope is left and how much of the broken down product is there. But other isotopes can be used to track chemical movement in living things, since living cells can't distinguish between 2 isotopes that are stable. But sophisticated medical technologies can. So it's a fairly common process to give a patient a certain isotope of whatever nutrient they're trying to track to see where it's ending up, to see if it's building up somewhere it's not supposed to, which helps diagnose different diseases. It helps learn new things about the internal functions of different organisms. But also, radiation is used to treat diseases like cancer when you're going into like radiation therapy, because it does give off the energy that damages certain cells. However, treatments like this do, of course, have their drawbacks, but it is helpful to treat these very aggressive diseases. Now, this is essentially where we're going to end our matter discussion today. Quick reminder that I am not a chemist or a physicist. I have a very basic understanding of chemistry and physics, and our video did not even scratch the surface of the classes that I have gone into. However, it does follow how in-depth the book that I am using for our intro-level general biology purposes does. And I hope to see you next week when we talk all about chemical bonds. Thank you again for watching this video. Don't forget to like, comment, subscribe, and ring that bell if you would like to see more. And if you'd like to follow me on any of my other social medias, the links are down in the description below. Don't forget to check out thereptilegoth.com for all of my articles and blog posts. If you found any value in this video and you would like to help support the channel, please check out my Patreon page. That link is also in the description down below. And a special thanks goes out to my Diamond Dragon patron, Diane V. What you're doing is really helping me fund a dream here. I will see you guys all in the next one.